Welcome to this demonstration of EcoStruxure Control Expert solutions to implement explicit messaging for the Modbus protocol using the general purpose library. This is the first part in a series of 2 videos dedicated to present some introductory concepts and examples on how to configure the Advantys STB and TM3 modules that will respond with the data requested by an MC80 controller. The second video presents examples on how to configure the GPL function blocks in the MC80 PLC for both Ethernet and serial communication. Please bear in mind that this is a basic demonstration, not intended to replace any formal product training. The user might also need to adapt the configuration shown to the actual project requirements. This presentation is structured in several chapters, each one started at the time indicated on this slide. The goal is to show examples on how an MC80 controller is collecting data from an Advantys STB island, from TM3 I/O modules, and from an M340 PLC. This solution could help to easily expand the I/O capability of the MC80 PLC. Of course, this procedure can also be used for the M340 and M580 controllers as well, for both Modbus serial and Modbus TCPU communication. The software for this demonstration is listed on this slide, using the most recent versions available at the time this video was prepared. Before we start our demonstration, let's briefly discuss when explicit messaging could be required or useful for your projects. When it comes to how communication between a PLC and its devices is configured, there are 2 main types, implicit or explicit messaging. In our Modicon controllers, we have implemented a communication service called I/O scanning, which is precisely an example of implicit messaging for Modbus TCP. In this case, the PLC will act as a Modbus client, which is equivalent to say that it is a Modbus master device. In certain Ethernet communication modules, particularly for Quantum and M340 controllers, implicit messaging is configured through an I/O scanning table, in which the user can add each connection required, along with the Modbus registers in the target device. This communication service is designed to read and to write to Modbus holding registers, which are addresses that start at 40,000 and will use Modbus function codes 3, 16, and 23. If the type of registers that the PLC application needs to read are input registers that start at 30,000, or you need to read bits or write to coils, then the function codes needed for this are not supported by I/O scanning, and you would configure explicit messaging, which is what this video is all about. In the M580 controller and some of Quantum and M340 Ethernet communication modules, instead of a single I/O scanning table for each module, the communication is configured for each device using a DTM library. The behavior of communication is exactly the same, it's still the same I/O scanning service. So here we see that implicit messaging is a solution that's very simple to implement. What you do is that you configure each line of I/O scanning, and you will specify the desired repetitive rate to update the data in the application, and then the PLC will completely take charge of handling communication, sending out the adequate number of Modbus requests, and there is no need to add any specific logic on the PLC program to trigger the Modbus messages. There is, of course, a maximum communication capacity on the CPU or the communication module, which is a combination of the number of input and output words, the maximum number of DIO connections, and the repetitive rate cannot be too short because there is a maximum capacity in packets per second. Now, although most communication modules of M340 and M580 EPACs do have I/O scanning, some of them do not include this service. More specifically, on the MC80 and M340 CPUs, I/O scanning is not available. Also, the Modbus serial communication module BMX NOM0200 does not have I/O scanning. So, another reason why you might require to configure explicit messaging is precisely in situations where I/O scanning service is not available on the products to be used in your project. Now, explicit messaging is implemented by several types of communication function blocks available in Control Expert. Readvar and writevar are used very frequently and support the Modbus function codes summarized on this table. There can also be less frequent situations in which other function codes are required, in which case you can use the data exchange function block. One important detail to consider when using explicit messaging is that there is a limit to the number of communication function blocks that can be active at any given time. This means that you might need to add some logic in the PLC program to control how many and when these function blocks are triggered, and perhaps even monitor the activity bit of the function blocks to see if their function is done or if communication is not yet complete. The whole reason behind this is that each CPU or communication module has a maximum capacity in the communication port buffer where messages are queued to be transmitted over the wire. To understand how many simultaneous function blocks are supported in each Modicon processor, we can check the specification for the maximum number of client requests per cycle, which are up to 4 in the case of the MC80 PLC, and up to 8 client requests for the standard M340 processor, which is part number BMX P341000. It is a maximum of 16 simultaneous function blocks for the performance type M340 processor, which are all the references except part number BMX P341000. Then for the M580 EPACs, it varies from 16 to 96, depending on the CPU model, and it will be a maximum of 16 for the BME NOC 301 and 311 communication modules, and also 16 for the BME NOC 0321 module. So the question this video will try to answer is, if you do need to implement explicit messaging, is there a pre-built function block in Control Expert that can make it easier to control how many messages are sent out the communication ports and still stay within the capacity of each module in terms of the maximum simultaneous client requests? The answer is yes. In the Control Expert General Purpose Library, or GPL for short, there are in fact several function blocks available for Modbus Explicit messaging. With the GPL, you usually combine two types of function blocks. One of them is the port profile function block, which is selected according to the maximum number of simultaneous explicit messaging requests. In this example, the Modbus Ethernet port M function block will limit the Modbus TCP client requests to a maximum of 4, which is precisely the capacity of an MC80 controller. If you were to use another model of CPU, you could select a port function block whose name ends with 16, 32, 48, 64, or 80, according to the number of simultaneous queries supported by the CPU or NOC module. The other type of profile is the client function block, which is called Modbus Ethernet Client for Modbus TCP. You would typically add several instances of this client function block, one for each group of registers that you need to read or write to, and each one of these instances will be linked to a single common port function block. For Modbus serial communication, we follow the same procedure, connecting a single port function block with several client function blocks whose messages are queued into the serial port. The names of the function blocks are just slightly different. In the case of the port profile, the function block is called Modbus Port M, while the client function block is called Modbus Client Basic. All of these function blocks are fully described in the Communication Components user guide of the Control Expert GPL. To summarize, let's compare each solution that we just discussed. If we take a look at the first line of this table, notice that implicit messaging is limited to Modbus function codes 3, 16, and 23. If you need to use other function codes, readvar and writevar can be configured for function codes 1, 2, 3, 4, 15, and 16, which by the way are the same function codes supported by the GPL function blocks. If you still need other function codes, then the data exchange function block could be the solution. Moving one line down in the table, you can see that I/O scanning is available in most CPUs and communication modules, but that is not the case with the MC80 or M340 CPUs. Explicit messaging, on the other hand, is available in almost all communication modules with a few exceptions mentioned in the table. Furthermore, if we want to know the maximum number of connections or messages that can be sent, in the case of I/O scanning, there is a maximum number of connections for a specific module, whereas for explicit messaging, the limitation is the maximum number of simultaneous client requests. As for the control the user can or must implement on each type of solution, with I/O scanning, you just need to configure a repetitive rate at a reasonable value to avoid flooding the network with very frequent messages, and be aware of the port capacity in terms of packets per second. For explicit messaging with writevar, readvar, and data exchange, the PLC logic must be designed in such a way to avoid exceeding the maximum number of client requests. This is done in a much easier way when using the GPL function blocks, because the port profile function block will manage a message queue and limit the number of simultaneous queries that are sent over the network. Lastly, it's always good to know if it's possible to change the PLC application online without requiring to stop the PLC. In the case of I/O scanning, generally speaking, this is not possible, except for the case of the M580 Hot Standby PLC, which has a special function block to allow installing a program built offline without stopping the PLC within certain conditions. When you are using readvar, writevar, or data exchange function blocks, online changes can be done on the PLC program. Finally, with the GPL explicit messaging function blocks for Modbus protocol, whenever you add an instance of these function blocks, it will usually be necessary to do an offline build and then download the program to the PLC, which requires to stop the PLC. That being said, if you're just modifying an existing client function block already in the program, an online change would seem possible according to the test I have done for this proof of concept when you are only changing a Modbus ID or modifying the index or the address for the Modbus registers. On this slide, you can see the sample architecture of the system that we will be using to demonstrate the use of the GPL function blocks for Modbus TCP with an MC80 controller. For this, we will use the Modbus Ethernet port M function block, which will manage the number of queries sent out of the Ethernet port. Then we will also use the serial port on the MC80 PLC, where the Modbus port M function block can help to limit the simultaneous requests to a maximum of 4. Now, since the total number of simultaneous client requests for the MC80 processor is 4, some strategy must be put in place to avoid all 4 queries on the Ethernet port sent out at the same time as the messages exchanged on the serial port. So for our example, a pair of timers will be used to schedule the activation of the function blocks. However, you could also reduce the number of simultaneous requests on the communication parameters of the port profile function blocks. Or another strategy could be to use logic to pass on the index or memory address of the registers to be read or written, and in this way limit the number of client instances that were added to the PLC program. With that, let's configure our system starting with an Advantys STB island, which will allow to expand the I/O capability of an MC80 controller. First of all, these are some of the resources available to download the Advantys STB configuration software, as well as several examples and FAQs. Bear in mind that I will be using a fixed IP address for the Modbus TCP communication module on the Advantys STB island, so the rotary switches are placed at the positions shown on this slide. So let's start configuring our project in the Advantys STB software. We will create a new workspace with a new island file name just called Panel 1 version 8. And then on our configuration, we're going to start adding, first of all, the Modbus communication module with dual ports. Next to that, we add a power supply. Then we will add a digital input module, part number 3615. Next to that, we will add a relay output module, 3210. And next to that, a 16 digital output module, and to finish the configuration, we will add the terminator plate. Next, we will start modifying the communication parameters by double-clicking on the communication module. We go to the Ethernet tab and select the Enable Editing feature. Here we will enter the IP address for our Advantys STB island with our required subnet mask, and then we will click on the Master IP tab to add the IP address of the master device, which in this case is the IP address of the MC80 controller. Notice the default hold-up time is 1 second. We will increase it to 5 seconds. This is the time before the Advantys STB goes to fallback mode. Lastly, we will click on the Redundancy tab in order to enable RSTP in case we want to do a connection in a ring configuration. We can then deselect the Enable Editing checkbox, in which case all the parameters are now protected from addition. And we have completed the communication parameters for our Modbus communication module. Going on with the rest of the modules, we will double-click on the digital input module to see what is the Modbus address that will give us the status of the inputs. Then we go to our 2 relay output module, where we can configure the behavior of the outputs, particularly the fallback settings when communication is lost with the main master device. In the first output, we will select the option to hold the last value that was written by the master device. The second output will keep a predefined value, which in this case will be a closed status. And then on the I/O image tab, we will have the Modbus registers. In the first case, the echo or the status of the outputs. The second register to actually write to the outputs from the master device. Lastly, on the 16 digital output module, we have the Modbus address that can be used to write the values to any of these outputs. Next, a very good way to review what are the Modbus addresses available in the project is with the I/O image overview, where you will have a list of all of the input and output Modbus addresses. It is also important to double check that the power supplies that have been added to the architecture will be capable of powering not only the modules themselves, but also the communication bus on the Advantys STB architecture. Once we have reviewed these details, we can proceed to build our configuration. Lastly, once the configuration is built, double check that in the message window at the bottom you have a build completed successfully message, in which case we will be ready to download the application into the Advantys STB island. Now we will proceed to modify the connection settings for the Advantys STB island to Ethernet, and we will also add the IP address that was previously configured for our Advantys STB island. Once we apply these settings, we can now proceed to connect to the Advantys STB island and download the application from our Advantys configuration software. Once the download is completed, the island is going to restart and take into effect the new configuration. And since we are connected to the Advantys island, you can click on the communication module to see the current status of the module. You can also do the same for the digital input module, double-click to see any diagnostic errors and the current value of the inputs as well. And as for the digital output modules, you can also double-click to see the current values in the I/O image tab. And finally, you can also check on the diagnostics tab any information regarding errors of communication or other problems with the module. Finally, I would like to share one more comment regarding the configuration of the timeout parameter in the Advantys STB, which is called the hold-up time. This timeout should be above any temporary halt in communication which you might expect in your control system. For example, in the architecture shown here, all distributor I/O and controllers communicate through switches in an Ethernet ring, which are using RSTP as a redundancy protocol. Should one of these cables linking the switches become disconnected, this might cause a topology change in the RSTP ring, and the switches must repopulate their CAM tables with the MAC addresses that can be reached at the corresponding ports. Depending on the number of switches, this process might require a few seconds in order to reestablish communication. Therefore, in the timeout settings that we use for this demonstration, the hold-up time for the Advantys STB Modbus TCP module was set at 5 seconds, which will help to avoid having its outputs switch to the configured fallback state if we just have a short interruption of communication on the Ethernet network. Lastly, the rate at which data is updated using explicit messaging is determined by the logic that triggers the communication function blocks in the master controller program. So you must also make sure that the Advantys STB hold-up time is greater than the frequency at which explicit messaging is activated in the master PLC. Now let's move on to the demonstration on how to configure TM3 modules to communicate over Modbus TCP. Here you will find some of the main resources available to download the TM3 configuration software and some great training videos. As before, I will be using a fixed IP address on the Modbus TCP communication header, and the roadie switches are set up as shown in this diagram onto the auto position. Once we have opened the TM3 bus coupler I/O configurator software, we will create a new project and then select the Modbus TCP option. Next, we will click on the module to immediately change the monitoring timeout from 1 to 5 seconds, which is the fallback time. If we click on the memory mapping table, it is still empty because we need to start adding the modules that are part of the architecture. So let's start by adding some digital input modules. We will select the first one in the list. It's an 8 digital input module, and then we scroll down the list to click on the Add button, which will make it appear underneath the bus coupler in the architecture. Next, we will also add some digital outputs. So we select on the list for digital outputs. In our case, it's the first one of the line for 8 relay outputs. Again, we press on the Add button to make it appear underneath the bus coupler. And we're now going to look for a mixed digital input and output module. Click again on Add, and now we are going to also add a mixed analog input and output module, the first on the list. Click on Add again. And lastly, we're going to add a safety specialty module that is part of this specific project. Now we can proceed to do some of the settings in the individual I/O modules. In this case, for the digital input and output module, we will change to functional mode number 2, which allows us to set up the behavior on the fallback conditions. For the first output, we will select to maintain or to hold the last value written, and next output, it will have a fallback value defined as 1, which means under fallback conditions, that output will be closed. In the case of analog I/O modules, you need to go and set up each one of the inputs with the range that you desire, in this case 4 to 20 milliamps. All the rest of the inputs will remain unused. And as for the outputs, the same thing, you need to enable them by selecting the type of output that you need, in this case 4 to 20 milliamps or 0 to 10 volts. Next, we can return to the configuration of the Ethernet bus coupler by clicking the first line at the top of the list. And now when we go to the memory mapping table, you will see a group of Modbus addresses that appear that will be available according to the settings that we just did in our individual I/O modules of the architecture. Then, to get more details on what exactly is included in these Modbus registers, you can click on the drop-down menu for each one of these groups of status, input, and output words. And the information that will appear here is going to be the result of the settings that we just did in our individual I/O modules. Now, the last thing we need to do is to save our configuration, and this will become a file on our engineering workstation on our computer, which will be then downloaded onto the TM3 system. Next step is to connect to the USB port of the TM3 bus coupler, and then open the embedded web page at address 90.0.0.1. It has a self-sign certificate, so you'll need to accept the risk and continue to open the embedded web page. If it's the first time you connect, you're going to need to type in the default username and password, which is administrator with capital A, both for username and password. Then the web page is going to request you to change the password to a new and different password. Now that we have logged on and changed the password, we can then simply open the existing configuration, which will be the project that we had previously configured with the I/O configurator software. Now we can click on Apply to download this configuration onto the TM3 bus coupler. Next and last step is to go to the Maintenance section on the Ethernet tab, and then change the settings on the IP address. In this case, we're going to use a fixed IP address, so we're going to give it an address of 192.168.10.30 with a mask of /24 and the respective gateway address. Now we can apply these new settings on the IP address for the bus coupler, and I would also suggest to enable the Rapid Spanning Tree Protocol, or RSTP, just because if you ever need to connect the bus coupler in an Ethernet ring, then RSTP would already be available. Use a bridge priority of a high value in order to have the bus coupler as a participant and not the root of RSTP. Apply the settings, and remember you will need to power cycle the TM3 bus coupler in order for these settings to come into effect. Lastly, in our demonstration, we also use a TM3 bus coupler for serial communication. After setting the baud rate to 19,200 bits per second with the rotary switch, the Modbus slave address was set to 6, as shown in the illustration of this slide. The procedure on how to use the settings on the rotary switch is clearly presented in the TM3 bus coupler hardware guide. We would then follow the same procedure by connecting to the USB port of the bus coupler and then load the configuration for the I/O modules using the same web interface. You might only notice some small differences in the options available on the web page. For example, instead of a tab to configure Ethernet communication, you would have a tab for the Modbus serial line parameters. Many thanks for taking the time for watching this video, which I trust will help you during the development of your projects. Please continue to view part 2 of this video, where you will see examples on how to configure explicit messaging for Modbus TCP and Modbus RTU using Control Expert's general purpose library.